This is the third lecture of 4 lectures on conservation of energy. In this lecture, we will concentrate on defining and learning how to calculate potential energy. Before we do that, let's distinguish between 2 types of forces, conservative and non-conservative. A conservative force is defined as this. The work it does is stored in the form of energy that can be released at a later time. For example, gravity. Gravity does, work on something only if it falls. But if the object is just being, held above the ground, we know that if we let go, gravity could do work on it and will do work on it. A non-conservative force is one that doesn't work that way. Friction is a non-conservative force. Friction is there, and it's only there when things are in contact, and it makes a difference only when objects are moving and in contact with each other. Also, work done by a conservative force moving an object around a closed path is 0. But that's not true for a conservative force. So what does that mean? Let's take this example. We have a box. So we're starting here at point A, and we're going to move the box from point A to point B. So if I asked you how much work was done by gravity moving it from A to B, mg would be perpendicular to that displacement AB, and the work done would be 0. Now, if I talk about the work done from B to C, I'm lifting it upwards and a height, and I'm doing work by a negative mg, so the work is negative mgh. And then if I move it to the west, from C to D, once again we have the same scenario where weight is not doing any work. And then if we ask how much work is being done by gravity or weight, moving from D to A back to its starting point, we see that it's moving downward, and gravity is working downward, so the work done is mgh. If we add up all those works, we get 0 as the answer, and that is the definition of a conservative force. Friction, on the other hand, is different. In this scenario, we see that in each case, we get a different amount of friction. No matter how we go, friction is going to do work on the system, and you're not going to get a total of 0. You're going to get a total amount of work done because it's always there, and it's always slowing the object down as long as it's in contact with the surface. Also, a conservative force, it doesn't matter what the path is. It doesn't have to be a rectangular path, right? It could be any path. If the force is conservative, the work is always going to be 0 along that total path. So if we pick up a ball and we put it on the shelf, we have done work on the ball. We can get that energy back if the ball falls back on the shelf, back off the shelf. In the meantime, we say the energy is stored as potential energy. So the work that we did lifting it is equal to its change in potential energy, but specifically, it's equal to its negative change in potential energy. So remember, we said before that work is equal to its positive change in kinetic energy. If I lift something up, I give it some potential energy, but if I let it fall down, it will lose its potential energy. Gravity will do work, but the work it does in making it fall is a negative loss in potential energy. But remember, it's also a positive gain in kinetic energy. So whatever it loses as it falls in potential energy, it will gain in kinetic energy. Gravitational potential energy is really easy to calculate. It is the gravitational force, the weight, times the height at that location, mgh. And the change in potential energy is going to be final minus initial, and the negative change is the opposite of that, initial minus final. So, we take a 1 kilogram ball and we raise it 2 meters. what is its change in potential energy, and how much work was done on the ball raising it. And then what would happen if it fell 2 meters. So delta U is UF minus UI, or MGHF minus MGHI. If I plug in my numbers, it started from the ground, so it has no height, so its initial MGH is 0. So I will get 20 joules as my change in potential energy lifting it. The work done on it by gravity during that process is going to be negative delta U, or negative 20 joules. If it falls, it would lose 20 joules of potential energy, but it would gain the same amount of kinetic energy. So delta U is positive 20 joules, and work is positive 20 joules as well. Springs are also conservative forces. They, think about it. A spring has a certain amount of elastic stored potential energy. And that elastic energy is going to be equal to the work done stretching it, 1/2 kx squared. So, for example, we have a spring with a constant of 20 newtons per meter, and it's stretched 0.5 meters. We want to know its change in elastic potential energy and how much work was done stretching it. So, if we find delta U, and we use our formula, 1/2 kx squared, we know that to start with, the spring wasn't stretched at all, so it had no potential energy. So UI is 0. When we plug in our numbers, we get 40 joules of potential energy gained when we stretched it. So when we stretched it, it gained 40 joules of potential energy. Of course, it lost 40 joules of kinetic energy at the same time. And the work done on it is equal to negative 40 joules.